Hey folks, my name is Matevz. I'm from the Oasis Protocol Foundation. And what Oasis is, well, we run a privacy-focused blockchain with support for also running off-chain applications inside the TEE. So this, for example, is a page where we have this validator agent off-chain application running. And we can notice some interesting information here. So the standard metadata like the version, the TEE, kind, the app ID starting with this ROFL 1. Then we have this hash of the enclave image running inside the TEE, who owns the application, how much tokens were staked in order to register it, and some other details. We also, for example, here have the secrets stored on-chain. So these secrets are end-to-end encrypted. In our case, this is Infura API key used to read from the Ethereum Sepolia in this case. And this user-specific keys can be stored as secrets on-chain, and then they are fed as environment variables when the application spins up. Okay, so this is the application that's registered on-chain. What's interesting here is that every application can have 0 or more active instances running on concrete hardware. So here we have one instance currently live. If we open it, we have the runtime attestation key that's generated each time the application is started, and the runtime encryption key for runtime-to-runtime communication. And then what I'd like to present here most is this metadata. So every replica, every TEE replica owns this data structure. This is all stored on-chain. And basically it's a simple key value store where only the replica can write to it and anyone can read. And you can store interesting things. For example, you can derive a key pair inside the TEE and then store the public version of the key inside this metadata. So in this case, there are two entries here. One is the ERC8004 V1 signing key. So this is up to application developer, how he would want to name the key. And in this case, this is used to submit transactions to Ethereum Sepolia. And then there's another public key here, and this one is used by Let's Encrypt. And when you open the website of this agent, this is the public key of the certificate that's actually issued, and you can then check whether the website that's rendered to you really originated from within the TEE, within the agent. Okay, so each Oasis app can have its own ERC8004 agent instance associated with. And now, how do we prove that the agent, some ERC8004 agent, is really running inside a TEE and that it derives the keys from the built-in key management service? So we need to prove two things. The first one is we need to audit the application source code so that the keys don't leak anywhere. I mean, if the key leaked, then there's no, the whole trust model fails, because, developer could just, post it and send it to himself and he would have all the private keys, right? So we need to audit the code. But not just the current version of the code, also any past versions of the code, because we allow upgrades of the application running inside a TEE, and the seed for deriving the keys is always the same regardless of the upgrades. So you need to also audit all the historic versions of any application instance that was running in the past. So a blockchain comes to the rescue here because it stores all historic data and all upgrades are public. And you can actually then verify that the compiled version of the enclave image really matched the on-chain version of the image registered at that point in time. Okay, but this is out of the scope for this presentation. I'd like to focus on the second thing we need to do. That's we need to prove that the current instance really runs the source code we audited, right? So when replica spins up, it runs the light client inside, it performs the on-chain registration and the attestation of the enclave, and then the app, it's then when the app can get access to the key management service. And similarly, if we want to verify, we need to verify all the steps by investigating on-chain data, from the consensus layer all the way down to this concrete application TE instance. But since we can't expect a user or an AI agent to actually run this whole process by himself, we combined the proposed ERC 8004 validation registry and built a validator agent. And it looks like this. So the idea is that when you make your TE application on Oasis, you also register an agent, and you store the Oasis app ID inside the agent metadata. So inside the identity registry. This blue rectangle here is the Ethereum Sepolia instance, for example, of the ERC 8004 registries, right? Okay. And then, for example, if we check the concrete example, there is this agent 1211, and there's this key net Oasis app ID, which has this hex value. And if we now decode the hex value, we see that this corresponds to some ROFL 1, app ID. Okay. And this app ID, so ends with U4P6K, should match what we have here, right? Yeah. So that's the validator agent ROFL application. Okay. The second step is, so when the TE application spins up, it needs to store, so it needs to generate the key pairs and then store the public versions of the keys inside this Oasis metadata structure we discussed in the beginning. And then the final step here for the TE application is to submit the validation request inside the validation registry. Okay, then what? Our validator agent listens to these requests, and if it is addressed to him, so to the validator agent, then it fetches ROFL metadata and computes the validation score. So in detail, basically what it does is it first checks whether the app ID stored inside the identity registry really exists on Oasis chain. Then it checks whether the application is running. So it checks whether these instances, these replicas here, are actually alive and working. And finally, it compiles the image from the source code and checks whether the enclave hash matches the one that's stored on-chain. So if everything is fine, then the validation score will be equal to 100. And also what it does is it copies this metadata here and stores them inside the validation response. So for example, let's take a look at our agent. So we have, this is the validation registry. If we query it, we have a number of validations here. Okay, let's just pick one and query it. So the validation score in this case is 100, so everything was fine. And if we move on and see the actual validation response transaction, so this is base64 encoded, and if we decode it, so this includes now the details of all the validation procedure. So we have the app ID, we have the score, and the most important thing here is we also keep a copy of this metadata. And in this case, the ERC 8004 V1 signing key, for example, if we're interested in this particular key, is here, and we can then verify, that we're really using the agent is really using this key, and we can verify the signatures if they match with this key. Okay, so what we just did is we presented how a user needs to check the validation response score, and if the desired public key is present there, and the user or the agent doesn't need to bother, doing all the on-chain complex steps to validate that some application is really running inside the TE and that their keys are really derived from within the TE. So we basically simplify these technicalities around the TE, but of course, one still needs to audit the actual source code so that none of the keys, leaked programmatically by the developer. Okay, thanks for watching and stay tuned.